Welcome back to this course, Econometrics. Today, we'll be dealing in module 6, limited dependent variable models. By way of module objectives, by the end of this module, students should be able to explain why OLS is often inappropriate for binary, categorical, and censored outcomes and identify the key problems it creates. Students should be able to state and interpret binary choice latent variable model. Students should be able to create log likelihood for logit and probit models. Students should be able to interpret logit probit coefficients correctly using old ratios. Students should be able to evaluate binary choice models using likelihood-based measures. Students should be able to specify the multinomial logit model for multi-category outcomes. Students should be able to explain the independence of irrelevant alternatives assumption. Students should be able to formulate the Tobit model for censored outcomes, derive its likelihood, and distinguish between effects on it. Students should be able to compute and interpret the Tobit marginal effect. Students should be able to design and report an applied LDV analysis with clear variation definitions. By way of introduction, in many econometric applications, the dependent variable is not a continuously measured outcomes that can take any real value. Instead, the outcome may be discrete, for example, employed or unemployed. It may be ordered, low, medium, high, satisfactory. It may be censored, expenditure cannot fall below zero, and many observations pile up at zero. Truncated, that is, only positive spenders are recorded. Bounded, a proportion between 0 and 1. These cases are called limited dependent variable models because the support of the dependent variable is limited by the data generating process, institutional rules, and the way the variable is recorded. Using ordinary least squares OLS in LDB settings often lead to problems that are not small technical details. The model can predict probabilities below 0 or above 1 in binary outcome settings. The relationship between regressor and outcomes is usually nonlinear, and the distribution of the error term implied by the OLS model is inconsistent, and the discrete or censored nature of the data. Most importantly, OLS coefficients in LDB settings may not have a meaningful interpretation, as marginal effects and standard measures such as arrow square do not summarize fits in any useful way. LDV models solve these problems by starting from probability models for the outcomes. The core idea is that an unobserved limited outcome is generated from an underlying latent, that is unobserved variable, that is continuous and follows an economically meaningful structural relationship. For binary choice, the latent variable can be interpreted as net utility or an index of profitability. For censored outcomes, it can be interpreted as desired demand or desired expenditure, observed only when it is above a censoring threshold. This model focuses on 3 central LDV families used throughout applied microeconomics, and policy evaluation. We have 1, binary choice models. We have 2, my multinomial choice models. We have 3, sensor regression models. Now, what are limited dependent variables? Like I said, they arise when the outcome variable has restricted support. That is, it's not a binary 0/1 category, or censored many zeros, or categorical multiple choices. Such outcomes violate key assumptions of the classical linear regression. Econometrics modeling must respect data generating process and support of Y. Why OLS fail in LDP settings? This is because there is predicted probability may fall below 0 or above 1. Errors may be heteroscedastic by construction in binary models. Linear specification impose constant marginal effects. Inference and interpretation become misleading. Latent variable framework, looking at the equation here. Y represents unobserved net benefit or utility. Observed outcomes depend on whether latent index crosses threshold. Probability models determined by distributional assumption on the error term. Looking at the logit model, this is the equation. This is derived assuming logistic distribution for the error term. This produces S-shaped probability curve. It ensures probability lies strictly between 0 and 1. The probit model. This is the equation for the probit model. It is derived assuming standard normal distribution of errors. It is similar interpretation to logic, but scaled differently. The choice between logit and probit usually not critical empirically. Then let's look at binary log likelihood function. This is the equation. The MLE chooses beta that maximizes probability of observed outcomes. No closed form solutions, numerical optimization required. Standard errors is derived from inverse information matrix. Logit odds interpretation, this is the equation. Coefficient of, that is Bj, represents change in logs odds. Exponential gives odds ratio. Odds ratio describe multiplicative changes in odds. Marginal effect, this is the equation. Marginal effect depends on x through p or z. Largest when probability is near 0.5. Report average marginal effect for clarity. Model fit and evaluation. Likelihood ratio test compares nested models. Pseudo arrow squared measures the relative improvement over null models. ROC curve and AUC measures classification performance. Multinomial outcomes. When Y has more than 2 categories, binary models are insufficient. Multinomial logic extend logic framework to multiple choices. It's also based on random utility maximization. Multinomial logic probability. This is the equation. Probability positive and sum to 1. It requires base category normalization. The interpretation is relative to base alternative. It is independence of irrelevant alternatives. Independence of irrelevant alternatives, RAA. Under here, relative odds between two alternatives independent of other options. It may be unrealistic if alternatives are close substitutes. It may be nested or mixed logit models. Relax IE. Let's look at censored outcomes and Tobit's model. Censoring occurs when values below threshold is recorded at boundaries, e.g. 0. OLS bias because 0 represent collapse latent value. Tobit combines participation and intensity in one likelihood. Let's look at the Tobit model specification. This is the equation. Latent outcomes observed only when above threshold. Error assumed normally distributed, estimated via maximum likelihood. Let's look at Tobit likelihood component. This is the equation. Censored observations contribute cumulative probability. Uncensored contributes density function. Likelihood sums information from both parts. Let's look at the Tobit marginal effect. This is the equation. Effect on observed outcome is scaled by probability of being censored. Interpretation differs from latent B coefficient. Participation and intensity effect intertwined. Let's look at two-part Hodel model alternative. In part 1, the logic probit probability of positive outcomes. In part 2 is the OLS or GML for positive values. It is useful when participation and intensity is determined separately. Let's look at censoring versus truncation. Censoring, this is all observations included, but some recorded at boundary. Truncation, these observations beyond threshold, not observed at all. Different likelihood structure is required. Let's look at the estimation summary. Binary and multinomial models is estimated via MLE. Tobit also estimated via MLE combining CDF and PDF terms. Robust or cluster standard errors often require here. For hypothesis testing, likelihood ratio test compares nested models. WAR test uses coefficient estimates and variance matrix. Last sample S-squared distribution applies. Common practical issues. There's perfect prediction, there is separation, there's rare event bias, then endogeneity not solved by no linear model alone. Applied example. Loan default binary. Interpret odd ratios and predictable probabilities. Transport mode choice, multinomial. This simulates policy impact on shares. Expenditures to zero, 2-bit. Interpret participation and intensity effects. By way of conclusion, limited dependent variables are essential whenever the outcome variable is binary, categorical, or censored. In these settings, econometric modeling must respect the support of data and the way outcomes are generated. Logit and Probit provide coherent probability models for binary outcomes estimated by maximum likelihood and interpreted through predicted probabilities, odd ratios, and marginal effects. Multinomial logic extends these ideas to multi-class choices, but requires careful attention to the IAA assumption and to interpretation via relative log odds and probability marginal effect. The Tobit model addresses censoring by combining a participation probability with a continuous outcome density within a single likelihood framework. Interpretation requires distinguishing effects on the latent outcomes from effects on the observed outcomes and the probability of being censored. Across all LDVs, strong empirical work depends on more than selecting the right estimator. Researchers must first define variables carefully, justify functional forms using economic theory, use robust inference when dependence or heteroscedasticity is plausible, and be transparent about causal limitation. When regressors are endogenous, non-linear models do not rescue causal interpretations. Credible identifications strategies remain necessary. Finally, reporting should emphasize economically meaningful quantities, probability changes, predicted category shares, and expected outcome effects rather than raw coefficients alone. That will be all for module 6. See you in module 7.